Okay, so we're going to start off modestly. We're simply going to build a two-stage pipeline. We're going to have one stage be the instruction fetch, and the next stage be the execution of the instruction that was fetched. And you say, okay, so that's two steps. So what's magic about this in terms of why is this performance better? The thing to realize, of course, is that while I'm executing one instruction, I'm fetching the next one in parallel. So the savings I'm getting is that the time it takes to do the instruction fetch is no longer added to the time it takes to execute an instruction. In other words, in terms of in our timing budget for how long a cycle takes. So we're going to have, in one cycle, we will in parallel both fetch an instruction and execute the one that we fetched in the previous cycle. And that means that our timing budget really just has to take into account the worst case of these two steps. It doesn't have to imagine they both have to happen in one cycle. They happen in separate cycles. So we're going to get a speed up out of this. We're going to be able to take the cost of the timing of the instruction fetch out of the budget for a single clock cycle. Everybody sort of understand the idea? So what we're going to do is we're going to add some registers here. So you can see this big gray stripe, and we're going to add some registers here, where the stripe crosses information that's flowing down the page. And you sort of look at this and say, fine, so to execute the instruction properly, I'm going to have its PC plus 4 because that's used by various instructions. LDR, or if I'm doing a branch, that PC plus 4 will need to store it in the register file. So I'm going to need that piece of information, and I'm certainly going to need the 32-bit representation of the instruction itself. I can hardly execute the instruction without the binary representation. And so that's, those are the registers we add here. And in general, one of the things we'll be doing as we do pipelining is adding more and more registers. Now, you may be a little puzzled about why we didn't put a register there. After all, it's a line that crosses, our pipelining arc. Aren't we supposed to put a register every place? The trouble is that information is flowing backwards up that line. Right? So in some sense, that's and there's a real problem there, and we're about ready to talk about that real problem. So the fact that there's no register here should be at least raise a warning. Either Chris has really porked it today, or there's probably something we need to deal with, because there's something that's happening in this stage that will affect what's happening in that stage, in the earlier stage. And so let's talk about what that is and how we can deal with it. So here's a picture of a pipeline diagram for the two-stage beta. And when we introduced these, I made a forward pointer to this lecture with the idea that pipeline diagrams will help us understand very nicely how a pipeline processor works. Remember how a pipeline diagram is organized. We have each of the pipeline stages as rows, and then as columns we have successive clock cycles. And we can tell for any particular clock cycle what each pipeline stage is working on. And so if I think about, I'm just going to follow execution here. So I fetch the ADC instruction. So that happens in cycle I. And in the next cycle, I'm going to be executing the ADC instruction in the execute stage. And while that's happening, I will be fetching the next instruction, the subc instruction, from memory. So those two things are happening concurrently in a single clock cycle. Notice that instructions basically sort of move diagonally through the diagram. So as we think of the instruction as it goes through stage by stage by stage, in other words, it's moving down row by row by row in a pipeline diagram, that motion happens one stage per clock cycle, so that the instruction effectively just marches diagonally down in our pipeline diagrams. And if all goes well, each instruction will basically just march through, and if we had a 5-stage pipeline diagram, we would have 5 different instructions all being executed in different stages of their execution, all in the same clock cycle. And if the gods were with us, maybe our processor would run 5 times faster. Right? If we could equally divide all the delay that we need to invest in the execution of an instruction, if we can divide it equally into 5 chunks, then our pipelining will actually get us quite a speed up. We're not going to be quite that lucky, but that's the basic idea. Okay, so this all works great. Everybody's going, great. This so far, Chris, no problem. Well, I hinted that the problem had to do with branches, and so what I would like to do is to now consider the execution of a program with a branch in it. So here's a simple little loop, an add, a compare, and then a branch back to the beginning of the loop. And let's see what happens here. So we start off fetching the add, that's great, and then while the add is executing, we fetch the compare, and while the compare is executing, we fetch the branch. So far, so good. And now the branch is executing. So this means that at this clock cycle is when we're actually thinking about we actually have the information from the register file. That's what, in the execute stage, we're going to go off and fetch RA, and the branch instruction wants to look at RA to see if it's 0 or non-zero. And so the decision about whether we're going to go back to the beginning of the loop or execute the XOR is being made in clock cycle I+3 for the first time through the loop. Okay, the difficulty is that if we're going to take the branch, do we want to execute the XOR? Right? No, that's, in general, if we're going to take this branch, we're going to go back to the beginning of the loop. It's a 3-instruction loop. We shouldn't really be executing the XOR until we exit the loop. It's the first instruction to be executed if we do not take the branch. However, what's our pipeline done for us? It's already gone off and fetched it. Right? Because it was busily doing its job, okay, before the branch decision was made. And so it's saying, okay, I'm getting the next instruction, yeah, XOR, XOR, XOR. And you're sort of going, wait, stop. We may or may not want to execute that XOR.